Good morning to all of you. In previous session, we have seen property of the Z transform, that is linearity property, and we have solved some examples on linearity property. We applied linearity property to identify the Z transform. So in today's session, we'll be discussing the time shifting property. So in case of time shifting property, if discrete time signal x of n has the Z transform capital X of Z, then if we are shifting this discrete time signal x of n by k samples, that is x of n minus k, we'll have the Z transform as z to the power minus k into x of z. Okay, so this is the time shifting property. If x of n having Z transform x of z, then this the shifted version of x of n, that is x of n minus k, will have the Z transform z to the power minus k into x of z. So the ROC, that is region of convergence of this Z transform, that is z to the power minus k into x of z, is the same as that of capital X of z, except for z is equals to 0 if k greater than 0 and z is equals to infinity if k is less than 0. Okay, so obviously this x of n will have the Z transform x of z, so it will have certain ROC, and if you compare the ROC of x of z and z to the power minus k into x of z, then the ROC of z to the power minus k into x of z will be the same as that of x of z, except for z is equals to 0. What does it mean? Except for z is equals to 0 if k is greater than 0, that means for positive values of k, right? So if k is positive, then if you are substituting z is equals to 0, so it will be 1 upon z to the power k, and this 1 upon, if I'm substituting value of z is equals to 0, so it will be 1 upon 0, and 1 upon 0 will be infinity. So that means z is equals to 0 will not be included in the ROC if k is positive, and if k is negative, so that means this sign will be plus, right? So it will be z to the power k simply, right? And if I'm substituting z is equals to infinity, then the whole value will be infinity. So therefore for negative values of k, z is equals to infinity will not be included in the ROC, right? So that is the time shifting property. If you are provided with x of n, it has the Z transform x of z, and then you can identify the uh, discrete time signal shifted by k samples Z transform simply by multiplying it with z to the power minus k. So this z to the power minus k, this k is nothing but the time variable with which this x of n has been shifted. This k can be positive or it can be negative. Okay, so we'll try to solve one example on this time shifting property. So here again, by applying the time shifting property, we have to determine the z transform of the signal x2 of n and x3 of n from the z transform of x1 of n. Okay, that means initially you have to identify the z transform of x1 of n, and from the z transform of x1 of n you have to determine the z transform of x2 of n and x3 of n by applying the time shifting property. So we have already seen that we can directly identify the Z transform of these signals, okay, by using Z transform formula. But here we have to apply the time shifting property to determine the Z transform of x2 of n and x2 of n from the Z transform of x1 of n. Okay, so the signal, discrete time signal x1 of n is given as what it is given as x1 of n is equals to 1 comma 2 comma 5 comma 7 comma 0 comma 1, right, with origin at 1. So the Z transform of x1 of n is, it will be denoted as x1 of z, and the formula will be summation n is equals to minus infinity to infinity x1 of n into z to the power minus n as per the Z transform formula, right. But here you can see that the limits of this n are from 0 to 1 2 3 4 5. It will be from 0 to 5 only. Okay, so this x1 of z can be simply written as summation n is equals to 0 to 5 x1 of n into z to the power minus n. So if I am substituting the values of n here, so it will be x1 of 0 into z to the power 0 plus x1 of 1 into z inverse plus x1 of 2 into z to the power minus 2 plus x1 of 3 into z to the power minus 3, then x1 of 4 into z to the power minus 4 plus x1 of 5 into z to the power minus 5. So if I am substituting these values of x1 of 0, so x1 of 0 is 1, right, so it will be 1, z to the power 0 will be 1, x1 of 1 is 2, so 2 z inverse will be there, right, plus x1 of 2 is 5, so 5 z to the power minus 2 will be there, x1 of 3 is 7, so 7 z to the power minus 3 will be there, then x1 of 4 is 0, this x1 of 4 is 0, so 0 multiplied by z to the power of minus 4 will be 0, and x1 of 5 is 1, so 1 multiplied by z to the power minus 5 will be z to the power minus 5. So this is the required Z transform of x1 of n. Okay, so it indicates the Z transform of x1 of n. So the ROC of this x1 of z will be entire Z plane, that means all values of z except z is equals to 0, because if I am substituting z is equals to 0, so it will be 1 upon 0, so it will be infinity. Even in this case, if I am substituting 0, so it will be 1 upon z square, right, so 1 upon 0 will be there, so it will be infinity. So x1 of z will be infinite for z is equals to 0, and for all other values it will have some finite value, even if I am substituting infinity. If I am substituting infinity, so it will be 1 upon infinity, and 1 upon infinity is 0, right. So now we have now identified the z transform of this x1 of n. Okay, so we identified the z transform of x1 of n as x1 of z. Okay, so from this z transform we have to identify the z transform of x2 of n and x3 of n. Okay, but what is the relationship between this x2 of n and x1 of n? So you can identify it from these given samples. So as we can see here, this x1 of n is having origin at 1, right, but this x2 of n has the origin at n is equals to 2, right. So here, sorry, you can say that if I'm comparing the value of n here, right? So you can say that this signal x2 of n is advanced, by two samples, right? Because here it is starting from n is equals to 0, then 1, 2, 3, 4, 5. Okay, so it is starting at n is equals to 0 and ending at 5. But now the origin is simply shifted at this n is equals to 2, that is at 5, right? So but if you compare the values of n here, so here it is starting with -2, then -1, this will be 0, then 1, 2 and 3. So that means this signal x2 of n is ending at 3, so it ends at 2 samples before compared to the x1 of n. So that means x2 of n is the advanced version of x1 of n. That means x2 of n is equals to x1 of n plus 2, right? So if I am advancing this signal by 2 samples, I will get this value, right? Similarly here, so this origin is shifted to left by 2 samples, so it has been delayed. Okay, so it is starting at n is equals to 0, then 1, 2, 3, 4, 5, 6, 7. So it is now ending at n is equals to 7. That means it is delayed by 2 sample compared to this x1 of n. So this x3 of n is delayed version of x1 of n, and it is delayed by 2 sample. Okay, so here we can write simply x2 of n is equals to what? x1 of n plus 1, right? Sorry, n plus 2. So it is the advanced version of x1 of n, while x3 of n is the delayed version of x1 of n. Okay, so it will have the z transform. So the z transform of x2 of n will be indicated as x2 of z, and the z transform of x3 of n will be indicated as x3 of z, right? So as per the time shifting property, what you can write here, so as per this time shifting property, if it is delayed by k sample, that means if you are identifying this a transform of x of n minus k, so you are multiplying this a transform of x of n with z to the power minus k. So here this n minus k is there, but in this case it is n plus 2 is there, so you will be simply multiplying the z transform of x1 of n, okay, that is x1 of z with z to the power k. Okay, because here the value of k is negative basically, so here you will multiply it with z square simply. So z square into x1 of z will be the value of x2 of z simply, right? Similarly, here you are dealing it by 2, right? So in place of k simply 2 is there, so it will be z to the power minus 2 into x1 of z. Okay, so it will be z to the power minus 2 into x1 of z, right? So this is how by applying. So here you can say that as per what time shifting property, as we know that this x2 of n, okay, x2 of n is the advanced version of x1 of n, that is x1 of n plus 2, and x3 of n is the delayed version of x1 of n, so that is x3 of n is equals to x1 of n minus 2. So simply the z transform of x2 of n and x3 of n can be identified from the z transform of x1 of n, that is x1 of z. So here you are simply multiplying this x1 of z with z square, and here you are multiplying it with z to the power minus 2. So therefore the z transform, here we can say that the z transform of x2 of n is denoted as x2 of z, and it will be z square multiplied by x1 of z. Okay, so z square multiplied by, we know that the value of x1 of z is 1 plus 2z inverse 1 plus 2z inverse plus 5z to the power minus 2 plus 7z to the power minus 3 plus z to the power minus 5. Okay, so if I'm multiplying it with z square, so it will be z square plus 2z plus 5 plus 7z inverse plus z to the power minus 3, right? So this is the required Z transform of signal x2 of n. Okay, so again the ROC will be same as that of x1 of z. Okay, that is entire z plane except for z is equals to 0. Okay. So as in this case we are written except for z is equals to 0, right? And z is equals to, we are seen here, right, in the property, if z is negative, that means it is z to the power k, that means it will be having positive power. Then for infinity also this transform has the value infinity. So for negative values of k, uh, the ROC does not contain z is equals to infinity, except for z is equals to 0 and z is equals to infinity. So if I can directly identify the ROC from this obtain x of z, x2 of z. So if I am substituting z is equals to infinity, so this infinity plus anything will be infinity, and if I am substituting z is equals to 0, so it will be 1 upon 0, so it will be again infinity, so infinity plus anything will be infinity. Okay. So the ROC will be the entire z plane except this z is equals to 0 and z is equals to infinity will not be included into the ROC. Right? Similarly, the z transform of x3 of n is, as per this time shifting property, it will be x3 of z and it will be z to the power minus 2 into x1 of z. Okay, to have identified here how this is z to the power minus 2 into x1 of z. So in place of x1 of z, we have to again substitute with this value, that is 1 plus 2z inverse plus 5z to the power minus 2 plus 2z inverse plus 5z to the power minus 2 plus 7z to the power minus 3 plus z to the power minus 5. Okay, so if I am multiplying this z to the power minus 2 with bracket, so I will get this z to the power minus 3 plus 2z to the power minus 4 plus 5z. This will be z to the power minus 2 only. Okay. So z to the power minus 2, z to the power minus 3, right? 5z to the power minus 4 plus 7z to the power minus 5 plus z to the power minus 7. Okay. So this is the required Z transform of signal x2, sorry, x3 of n. Okay. So this is the Z transform of x3 of n. Again, ROC will be the same as that of x1 of z, except, so ROC will be entire z plane except or z is equals to 0. Okay. So again, here the value of k is positive, right, as per time shifting property. So z is equals to 0 will not be included. Even you can identify it from this z transform. If I'm substituting 0, so it will be 1 upon 0, so it will be infinity, right? So z is equals to 0 will not be included in the ROC. If I'm substituting infinity, so it will be 1 upon infinity square or 1 upon z square, so it will be 1 upon infinity, so 1 upon infinity is 0, right? So z is equals to infinity will be included in ROC, but z is equals to 0 will not be included in ROC, right? So this is as per this ROC of x1 of z. So it is same as that of x1 of z. Okay, so x3 of z has the same ROC as that of x1 of z, that is entire z plane except for z is equals to 0, right? So this is how you can use time shifting property for identifying the Z transform from the given signal cell transform. Okay. So in today's session we discuss time shifting property. If x of n has the Z transform x of z, then x of n minus k will have the Z transform z to the power minus k into x of z, right? And depending on the value of k, whether it is negative or positive, its ROC will be modified, right? So here one signal was given, that is x1 of n. From the Z transform of x1 of n, we identified the Z transform of x2 of n and x3 of n by applying the time shifting property. Okay. So in next session, we'll be discussing another property, that is scaling in the Z domain. Right. So thank you for joining this session.